trying to think of the, let me give you the example of the short to ground, the Viper alarm, the 900 ohm short to ground example. That's really what I'm thinking about here when starting on our highest scale and how important that is. So you guys don't need to know a lot about this yet to understand this case study. I have an ignition control module and I have an engine control module, and these two guys are talking to each other. The signal that's on this wire is a 0 to 5 volt square wave. Okay? Where this signal comes from would be from a crankshaft position sensor signal that comes in. It's actually an AC sine wave that gets converted to a digital before it gets sent to the engine computer. The engine computer with that signal will take and it will calculate the RPM and it will do things with that. It also tells the computer piston position and location, and some of the things the computer will do is it will control the injectors based off of this on-off square wave. Okay? Questions so far? You don't need to know the hows as much as you do just this basic concept that the crankshaft position sensor creates a signal, the ignition control module converts it, the engine computer watches it and controls the injectors. Okay? This particular, we're not on, actually I'm just emphasizing this page and meter hookups is my intent with this. Okay? On why we want our meter connected like this and where we could go wrong if we do it incorrectly. So we have the right perspective. The other thing that the ignition control module would do is control the spark on this design. So the spark is controlled directly by the module and the computer is controlling the injection pulse. Without going too deep into this, I know some of you probably have this question, well wait, what about electronic spark timing? There is another circuit that I don't want to talk about right now that the computer is talking back to this ICM to tell it what to do with the spark at certain times. So yes, the computer is controlling the spark as well. Here's the symptoms with the car. It has good spark and no injection pulse. Okay? So what do we know is good to begin with without doing any tests at all? The ICM is good. I would agree, because the ICM is the one that's controlling the coil directly. It's being told what to do at times. There's a switching mechanism. It has its own little microprocessor inside of it that does some decision making on its own. And then there's one of these guys here too, and they'll talk to each other.
Is it possible the input coming out of the ICM to the ECM is incorrect?
That is exactly where we are. You are a smart character. That's where we are. So my process here would be, well, let's back up for a second. We missed something. The ICM is good. I think would all agree the power ground is good for the ICM. If the coils are firing, you might have some questions on that, but you'll have to wait till we do ignition systems more, and I'll fill in those gaps. We could also say the crankshaft position sensor is good. Wouldn't you agree? For the coil to fire, there has to be some type of timing signal coming in. It cannot fire on its own. We need to have an input. The output is there. The input needs to be there as well. Crankshaft position sensor signal is also good. So with no injection pulse and the car does not start, we are concerned, our focus is on our engine computer and it is on our injectors, but we can't forget that the engine computer also needs an input to know when to fire the injectors, and that would be the signal that Rob just mentioned, this 0.5 volt square wave. It is known as the reference signal on GMs. It's a reference signal, and they've named it that for 20 plus years, so it wouldn't be, see Rob's writing stuff down, so it wouldn't be a bad idea for you to write down the name reference. It'll be a shortcut for later on what wires what. So here's what I'm going to do with this setup is I'm going to check for that reference pulse. Even though the spark is there, we cannot assume that that digital signal here is there. So I connect my scope up like this, back probe the ignition module on a voltage scale, and I go to ground, and what I'm looking for is this 0 to 5 volt square wave. And what I see on my scope screen, and my default for the particular scope I was using, which was the Vantage Snap-on Vantage, not the Vantage Pro, the older graphing meter, I was set up on a 0 to 14 volt scale, so definitely enough to see it. And here's what I saw on the bottom of the screen, 0 volt flat line. That made sense to me that I am missing this input. And why we don't have injection pulse, it makes sense why we don't have injection pulse. I learned this procedure years ago, and it was actually from the Snap-on troubleshooter on what to do next, and the procedure that some other technician developed, and it was the first time I ever did something called a bypass test, and then I kind of ran with it, and you'll find out here coming up in sections 2 and 3 that bypass testing is one of my favorite things to do for troubleshooting. But here's the test. We take a test light, and we connect it to battery positive here, and we touch it on and off of that signal wire. We have to have the key on. We need the key on because we need to have the engine computer powered up because we need it to react. Take a test light, touch it on and off that wire, and the injectors should fire if the engine computer is good. We're creating this signal, and I did that test, and it worked. The injectors fired. How is my signal wire? How is my computer? How are my injectors that it reacted like it should have? It says they're all good. And so the method would be to replace the ignition module. Even though it had good spark, this module does other things than just control spark. It also sends and converts this AC signal to digital and sends it this way, and things get interrupted in these GM modules. I have done this over 100 times, probably at this particular juncture when I had this case study. 100 different modules, GMs, where we have no injection pulse and we have good spark. Kind of odd to say I have a bad ignition control module when you have good spark, but that was what failed inside of these. So did the test. The old troubleshooter in the Snap-on scanner, they called it a scratch test. And I just remember that test vividly. One of the things you wouldn't want to see, a bad scratch test where we're touching this on and off and looking for a reaction, a bad test would be when you touch on and off of this, nothing happens, no injection pulse. Where does that move us away from when we don't have a reaction? Let me back up. When we're troubleshooting and we're trying to find direction, we're always looking for tests that say, I'm going to turn left or right. And I've started using this in an analogy the past couple of years, and I think it works really well. I'm always looking for something that I can eliminate this bunch of variables, and then I'll walk down this road, which narrows the possibilities. Because right now, we have this whole mess of things it could be. Crank sensor, module, wiring, computer, injectors, fuses, and so on. Some of this we use some knowledge and theory, and it's hard, I know, in here, and it's easier to see it, but how important is the theory in this application? I know the crank sensor signal needs to be there for spark to take place, so just because I know the theory, I don't need to check the crank sensor. Anyway, this particular test that I've done is I am at a fork in the road, I'm turning left or I'm turning right. If I touch this test light on and off of here and I get a reaction, I'm turning right. If I touch this test light on and off here and I don't get a reaction, I'm turning left. And I have two separate groups of variables within this turn. Does that make sense? This is troubleshooting. This is what's in here when I'm doing it. I'm turning left, I'm turning right. And I started to convey that. It took me, I think, years to figure that out, and I think it helps to have that perspective. What are we doing? Where are we going? You're following a map, you have a compass, this road's going that way, that road's going this way. I need something, hard evidence that will give me a direction. I need to go this way or I'm going this way. That doesn't mean you're always going to be right in that direction. You're going to go left and take a couple more steps and be like, I need to back up to that point again. And let's revisit that. And oh crap, that's what I did wrong. Let's go right now. That happens all the time. That's where we are here. I gave you the reaction, the example. In my case, the injectors fired. That says what about the computer, the wiring, the injectors? It says what? They're good, so do you see my focus is to the left, which is the ignition module. Why is the module not sending that signal? I can create that signal. Okay. If I did that test and it didn't react, I had no reaction over here, does it make sense that I wouldn't turn left and focus over here? Because I'm creating the signal that the crank and module together would create, which is this square wave. I'm creating that signal and nothing's happening over here, so my focus is over here, not over there. Two completely different directions we go with one simple click, click of the test light. Okay, so I told the garage owner, and I've done this 100 times, change the module. He got paid my $70 and I was happy, and this was money. This is money right here to me. I know this system like the back of my hand, you know? He calls me up later in the afternoon and says, hey, the truck's still not starting. And I said, there's no way. There's no way. I know it's going to run. Put another module in it. You got a bad module out of the box. I've seen that happen. A bad ignition module right out of the box. It's not common, but it does happen. So I told him to put another module in it. He calls me back later in the day. The truck's still not running. I got to go back. So I go back and look at the truck. By the way, I don't charge for those. If I got to go back, I got to eat it, however long it takes now. So I go back to the truck and I redo these tests, and same thing. I'm like, wait, why is the test light working? And when I connect my scope, I don't have a signal. And I thought about a short to ground. You see where we are now. There is a point of this story where we're on short to ground testing. I thought of a short to ground, but I thought that if my wire was shorted to ground, that let's draw a short in here. If this wire was touching ground, when I did this test, my test light would have lit when I connected it. And that's the part of this troubleshooting procedure, was if the test light lights, the wire is shorted to ground. These circuits that you're creating, these signals, are really between some chips here. They don't support current flow that test light would carry. And the test light did not light. So I said, that wire's not shorted to ground. Made the call, but where's my signal? So here's what I did next. I took my scope, because I saw something here. I looked close this time because it wasn't making sense. I could make it fire the injectors with my test light. Test light was not lighting. This wasn't there, but I still didn't have a signal. And I looked real close at my scope, and I was seeing these like thicker lines down at the bottom of my scale. So I changed my scaling. I took that same screen, and I'll teach you guys this as we go. I changed it to a 0.5 or maybe a 0.1. I don't remember. I think it was a 0.1 to see it. And that same signal now, I see this on the bottom of my screen. Is there a signal there? There is. Why didn't I see it on my 14 volt scale? Yeah, it's just too small of a waveform. So there's something there. And after I saw that, I thought, well, maybe there's resistance in the circuit, or I don't remember my next step, but I definitely am going to now, really this is where the manufacturer flowchart would have been better. Manufacturer flowchart would have had you disconnect the module, disconnect the computer, and measure the wire for opens and shorts. And that's really what we need to do at this point. So this will be a good review of that. My concern is not an open. And you guys will learn this as we go, and I'll repeat this over and over. If I had an open circuit here, I'd still have a signal here, but it would not be here. And I have no signal coming out of this module. So an open is not my concern. A short to ground is my concern. When we do a short to ground test, this is where we are. How do we handle that? Let's get rid of some of this. I want to do a short to ground test on this wire. What do we have to do? What's the method? You guys should know this from your basic electrical class. If you don't, it's okay.
I know.
That's why we're doing it. Yes. Start to finish. What do we do first? The first answer is not anything with the meter. We have to do something with that circuit first. Mm-mm. Nope. Visual is always good, and a load would come in when we're doing voltage measurements. We're done with that now. A perspective you guys need to have with your ohm meters. Your ohm meter is the battery. When you do ohm testing, you have to have the perspective that this ohm meter is my battery for this test. So now any other voltage source cannot be there when we're using the ohm meter. So we need to isolate the circuit. We need to disconnect both ends here and here to do proper resistance measurements. Because what can happen is if you don't isolate the circuit, we can get back feeds that go the other way and find their way back to the meter and give you false readings. Okay? More so with the short to ground test, it is very, very important that I disconnect the module here and that I disconnect the engine computer here. And I want to measure that wire for a short to ground. This is the test I want to do. I know some of you might be thinking, but wait, your test light didn't light. You're right, it didn't light, so we can't have a short to ground. That is incorrect. We could have a partial short to ground. That would be not enough to light the test light, but enough to pull that signal down. Let's do the test and I'll expand on that. Ohm meter, where do the leads go? First step.
Each end of the wire.
Each end of the wire would be incorrect, and that would be what everyone typically says, so that's okay that you, is it Matt? It's okay that you said that. That is an open circuit test. And remember, going into this, we were never concerned about an open circuit. We were concerned about a short to ground. So let's follow this through. Let's say that we go this path, and if we go end to end, even if this wire is shorted to ground, what will that ohm meter do? How does it react? How does it read? It sends out a small trace through the circuit. It's not driven to go that way. Where's the return path for these little electrons? The meter. And so the ohm meter will read what? The ohm meter will read 0 ohms, which in this case, you would say to yourself, there is continuity through that wire, and that's a good wire. And our problem is within this wire the whole time. Okay? We would miss it. And if your next step was to replace the module, let's put, this module is only 80 bucks, right? Let's say it's a $2,000 Subaru engine computer. $2,000 mistake. You were right there. You had everything going on. I don't mean to pick on you, Matt. This is typical. You were right there. You followed the whole process, and you just simply put your ohm meter lead in the wrong location for the test you were trying to do. How important is this? So that is incorrect for a short to ground test. What we need to do for a short to ground test.
Can you put it on the body somewhere?
Yes, absolutely. One lead, doesn't matter which one. Ohm meters are not polarity sensitive either. There is no red and black lead. There is red and black leads, but they are not polarity sensitive. It doesn't matter if you hook it up one way or the other. Well, it does for diodes, but that's different. Those are check valves. For a regular circuit, it doesn't matter. You will never read negative ohms, regardless of how you connect your leads. One lead's got to go to the wire, and the other lead has to go to something metal on the car. The whole body of the car is your, quote, ground.
Does it matter where? I mean,
no.
It really doesn't.
Yes, it actually does.
Say it ought
You want
I've done this where most of the stuff under the dash, for example, is very good, but then I connected my meter up to this metal bar under the dash, not realizing that both ends of that metal bar were bolted to plastic.
Yeah.
Because it was some part of the AC housing inside, and it wasn't a ground.
Okay.
So we have to be careful of that.
But in theory, if this were, in theory, an entirely metal car,
Yes,
it would be
anywhere.
on one corner and be on the other
Anywhere
corner,
on the
and it
car.
would read fine.
Yep.
This test would be valid.
Yep.
Okay.
Anywhere on the car. Be careful of rubber mounts.
Sure.
Stay away from those dog bone mounts on the front of an engine where there's clearly rubber boots and grommets in between. Stay away from stuff like that. But yeah, anything metal on the car, and it's got to be clean metal too. And if you were smart, what you would do, just like checking our ground for our meter, we would connect this to a location, and then I would take this lead and I would touch this next to the wire where I'm testing, I would touch another part of the metal of the car to make sure what? That one's good. What will my meter read when I do that? If I'm touching metal on this side and I'm touching metal up here, it should read 0 ohms, right? That tells you that's good. Now you can do your test. We should always be thinking along those lines, especially if we're ready to make a $2,000 call and it's one simple mistake that will blow that. So now we're ready to do the test. What scale do we want to be on?
The lowest possible.
For a short to ground test, we want to be on our highest one, because on a good wire, here's what the meter should do. On a good wire, this meter should send out a trace and it has nowhere to go. And so the auto range feature of the meter will jack you up to the next highest scale, to the next highest scale. It'll go all the way up to M ohms. And the only true infinity would be on this meter is OL M ohms is what we should read for a no short to ground test. We want to be on our highest scale here in this case. Questions on that?
It'll skip right past the highest scale.
It'll move itself all the way up to the highest scale. In fact, when you start, as soon as you turn your ohm meter on, Rob, it'll always be on the highest scale.
Okay.
Because the leads aren't connected to anything and there's nowhere for them to go. So as soon as you turn your auto ranging meter on, it'll be on the mega ohm scale. And it'll work its way down as that number is changing. But if you weren't on an auto ranging scale, think about this old school meter. You know, you don't have to go buy a fancy meter. Some of the meters, they don't have auto ranging scales and you have to select them. So in this scenario, is it important that I understand these concepts and that I make sure that I'm on the 20M scale, not the 200 scale? Because if I'm on the 200 scale, I might miss it. Here's what we have. This car has a Viper alarm system wired into it that I did not know was there, and the owner did not know was there. It was a work van, and I found that alarm system in the process of disconnecting the computer to do my short to ground test. I'm following the harness and I see this purple white wire, which is my reference wire, and I see this splice going into it, and I'm like, missed it. I knew right there where my problem was, right? So this Viper alarm was the equivalent of a 900 ohm short to ground, 900 ohms. And what would this alarm, how did this alarm system work? When it was going off, it would short that circuit to ground, not a full short, but enough to take that square wave that was supposed to be a 5 volt square wave and drop it down to a 0 to like 200 millivolt square wave, enough that it would not be able to be seen and it would cut the injection pulse. Pretty neat system.
And that's actually how those work.
That's how that one was designed.
So you didn't have a bleeper.
Yeah, you didn't even know it was there.
But I'm saying,
Yeah, I did not have a way to deactivate it.
had you a bleeper, you could have.
I just cut that wire and fixed that, and there you go. The car started up. That was the fix.
But he wasn't carrying like the key fob.
No, he didn't even know it was there. He bought the van. He had the van for a couple years, and the thing just activated.
Awesome.
Right? All right, but back to the resistance measurement. Do you understand if I would have picked on this meter right here, if I would have done this short to ground test and started on my lowest scale, which is 200 ohms, my meter, well, there's no battery in there. My meter would have said OL, and I would have said what? Maybe, not thinking about the wire. The wire's good. You guys with me on the statement I have in section 1, which is a foundational statement. If you're doing short to ground testing, what page is that? 23. If you're doing short to ground testing, make sure you're on your highest scale if you're using a non-auto ranging meter, or if you change your meter from an auto range. There's another issue here, guys. On the highest ohm scale, what is going to happen if you touch your leads is the meter will travel the electrons through your arms and you'll get a reading. If you go end to end with your leads, you'll have around 200 to 400,000 ohms of resistance on average. If I would hold the positive lead here and hold the negative lead here, So imagine that you're connected to a ground and you're touching the lead as you're touching maybe your T-pin or whatever it is you're measuring, and you want it to be OLM ohms, right, the highest scale, and what's happening is you're getting some reading on your meter. What is it doing? It's traveling through your finger, up your arm, across your chest, down your other arm, giving you a reading on the meter. So on your mega ohm scales, don't touch the leads. That's all. Most of the time, that's a non-issue. You guys understand on our 12-volt systems, it's a non-issue. Doing voltage measurements, touching your leads. Go ahead. You're not going to get electrocuted. You have too much resistance in your body. Or even measuring a resistor that has, we'll use that 12.6 ohm number again. If I'm measuring this particular fuel injector and I put a lead here and here, I almost have to, because the top of that injector looks like this, and I have to hold my leads on those terminals. Is that going to interfere with your reading? Mathematically, yes, but it's so small that it doesn't change the number. It still would read 12.6 regardless of your body having, say, 400,000 ohms. This is Ohm's law. I didn't expect to do this, but it's, if you had a resistor here and another, let's see, this would be in parallel. Remember your parallel laws. And I have another resistor here, like this. It's a parallel circuit. If this is a 12 ohm injector and this is a 12 ohm injector, if I put my meter here and here, what's the reading?
12 ohms.
It's not.
Wait, what did you say? Total resistance.
What's total resistance here? It would be 24 if it was this way.
Yeah, no.
Oh wait, it's
Six.
Yes.
Ah, that's right.
This would be 24. This one is 6. So without going through all of that, here was my point. If I measure this injector that's 12 ohms, picture the coil, right? It's down inside of here. I can't draw three-dimensionally. That sucks really bad. And then you're holding your leads, and so it's really, your body is involved here too, and you got resistance here too with your body. Don't you have this going on? You do. However, let's do the math on this one. We're going to need a calculator. 12, we'll just use 12, okay? 12 and 400,000.
No.
There are some parallel laws. Hold on. Parallel laws. The total resistance will always be what? See how much you retained. Higher than or lower than the lowest resistor in the circuit? Always lower than the lowest resistance. There's some common sense to that. The reason I tell you right now that the number will be less than 12 because we have an alternate path for current to flow. Even though it's a real high resistance path, total resistance would still be less than 12. What is it?
A lot less than 12.
11.9, what? Is it?
You're dividing 12 by that. So
Well, to do total circuit resistance on this, there's some different factors, and there's different formulas in figuring this out. I didn't want to do this.
Do it.
I can't remember. That's why. Put me on the spot. It was, this is probably, there's 5 different methods of calculating this. One of them we did already, which was taking the number of equal resistances and adding them together and dividing them by the number of, that's the easy one, right? There's another one that's R1 times R2 over R1 plus R2, or do I have that backwards? Do you guys remember? That would be the way that's done.
Find the reciprocal.
Well, you take these two, and then you divide your, let's just do it. Give me 12 times 400,000.
4.8 million.
Is it that high?
Parallel, yeah.
4,800,000.
4,800,000.
But hold on.
I might have the times. It might be R1 plus R2. I might have these inverted. I told you it's been a while.
On that right now. I want something
Well,
you said
just,
30 seconds ago.
oh, what?
How you said you take them and then you add them together
I
and then
have
you
it
divide.
right now.
There's 5 different methods is what
Yeah, but for the one in the middle, you said you take them.
Oh, this one?
Yeah, that would give you an
Add
answer.
One of the
You would get 12.
well,
That's
okay, let me back up to the easy method.
Here's how to do it.
Okay, just hold that thought for 1 second. I want to address the easy method because Jackie's question is relevant to our fuel injection systems where we have a group of 3 injectors or we have a group of 6 injectors and they're all fired together. So if I had, let's do this. If I had a resistor here and a resistor here and these 2 guys are 12 each, right? This group is going to be a total of 6. This is a 6 ohm circuit. If I have, and I'll tell you why in a second. If I have 1, 2, 3 12 ohm injectors, then this is, if my math is right, this is a 4 ohm circuit.
So then you're not adding them together and then dividing.
Well, you're adding the number of resistors that have the same value,
Right.
which is 3.
You're
That's
not
the,
adding the ohms, is what I'm saying.
no, I'm not. I'm
Okay.
taking,
That's what I thought.
there's R1, R2, and R3, and I'm adding, those are all the same number.
Right.
So, yeah,
Right,
that's,
what-
okay. Does that make
I thought
sense?
You were trying to say like, oh, you're adding 12 and 12 and getting 24 and then you're dividing
No.
by 2 because there's 2 resistors.
No,
That's
I don't know if that would work like that. It
It
may.
would. That's why I was saying I'm
Oh.
confused because I
Yeah, gotcha.
Well, yeah, that's not what I remember.
There's different methods, Tom. What do you have when you Google search that? Is the multiplication underneath?
What
It's-
this is saying
it's-
for parallel resistance,
It's either
total
this.
resistance is equal to 1 over, and then there's a
That's a method I didn't want to do. That's the one with fractions, and it's 1 over R1 over. I don't want to do that one. There's another one that I'm looking for, and it's this one. When you have 2 resistors, you can use this one. It's more simplified. But here's what I don't remember, Tom. I don't remember if the plus is on the top or if the plus is on the bottom. You with me?
I think it's gonna be on
It-
the, I think it's on the bottom because I did it.
Yes.
Like the one on the bottom and it comes out to be 11.999.
That's what I'm talking about. So what was that you did? It was you used this right here, and then here's how we would do it. R1 times R2, which is this number, 4,800,000, and then it's R1 plus R2, which is 412,000 ohms, and you take that number divided by that number, and you come up with what?
11.99964.
Do you guys understand? Here's my point. That was a roundabout way or the math way to tell you guys that when you're measuring low ohm circuits and your body is involved, don't worry about it. That was my whole point.
it's a high resistance one you don't worry about.
It's such a small change that won't make the determination. And is that meter going to read it anyway? Is that meter going to read 12? At 11.99964, the meter never moved.
You're rounding up for 4 decimal places.
That is correct. But is your body involved?
Well, yeah,
It's there. You're not seeing it.
technically it's there, but it's not.
And it is changing the number, but it's so small it doesn't matter. Is there a time that would matter? Yep.
Yep.
Very high resistance.
I have seen circuits where your body's involved. You got this 12 volt feed. Let's just use a light bulb. This light bulb does not light. Student's car. Take that wire off, you disconnect the connector, so you unplug it, and you read 12 volts on here with your meter. So your meter's connected like this to ground. That's a good feed, right? But then as soon as you touch that lead, that voltage on your meter drops down to 5. What did you just provide?
A resistance in the.
You just provided a load for some electrons to move. Even though your body's real high resistance, that corrosion that's in that wire is so bad that even your body connected would have that effect. Or that probably wasn't as accurate. If it was that bad, your meter itself, the meter has how many million ohms between here and here? On a voltmeter, on a good voltmeter.
40?
Nope. 10 mega ohms of impedance is what all these meters say. What does that mean? That means between the positive and negative lead, there's the equivalent of 10 million ohms of resistance. The meter itself can be a draw on the system. Let's see if this makes sense. I connect to that circuit, and it would seem to contradict what I said yesterday, which is the circuit has to be loaded to see a voltage drop. That would be the point. And there are certain circuits that have so much resistance that your voltmeter itself will draw the voltage down when you connect to it. So in this scenario, that resistance is so bad that even this 10 mega ohm impedance meter, remember the bulb's disconnected. There's nowhere for current to travel. As soon as I connect my meter up to this, it reads, let's say 5 volts. Going to ground. Why? How can we justify that? That contradicts what I told you yesterday. It doesn't. Your meter's the path. And that resistance over here is so bad that your voltmeter is reading a lower voltage because the meter itself is causing it. If I could disconnect my meter and have x-ray vision and look into that wire right there, I promise you it would be 12 volts. I don't care what that resistance number is. But because you connected your meter up to that, and that resistance over there is so high, in the probably millions of ohms, as soon as you connect that meter up, it causes a current draw through your meter. Yeah, how much? It's 10 mega ohms of impedance. Not much, but enough to cause a voltage drop. Don't count on that. Don't do disconnected circuit tests, but I'm just painting another picture for you as variables on what can happen. And what might seem like a contradiction is not a contradiction. You're probably thinking, I will never see that. You are totally wrong.
I'm thinking I need to see this to fully grasp what the hell it is.
I could show it to you in a video. I have a video of a low voltage circuit where I connect my meter. It's 450
Is it actually
and
of you doing stuff, or are you just recording the own meter? Because I need to see it.
I'm trying to think of the case study. It's a case study video, but yeah, they're definitely there.
How are you guys so close? I'm serious. Like I just put my foot under my chair and I hit his boot.
I don't know. That's a good question. That's something that I have talked about countless times in some of my case studies and pointed it out. And I don't know if I ever really had the chance to explain it like I just did now. So this will be one of those in hindsight things when down the road if you're watching my videos, you should be. Although you should be watching them at lunch, on your break. It should be scanner danner in your head the whole time you're here. When you're watching some of these case study videos I have, you're going to hear me talk about, oh, that's the impedance of the meter causing that. And I've had these questions where people are like, what the hell are you talking about? This is what I'm talking about.
But I'm saying, do you show it?
Yes,
Okay.
I do. Not intentionally. As I'm going through a troubleshooting process, I'll run into this and be like, oh, that's what this is. That's why it's doing that.
Yeah, I don't want to just watch a video of a screen.
It's not. It's an actual case study where I'm following you through. I don't know offhand which one I could point you to toward that.
You can think about it at a break.
Okay. Questions on the short to ground test, or the ohm meter, or the your body for open circuit tests, or the low ohm readings? No concerns there. High ohm readings, we are concerned, right? Don't touch your leads. And this phenomenon here. Sorry. Okay, go take a break.